Welcome to Last Week in Science. I'm your host, William Logian, and on today's episode, I'm talking about quantum computing. What is it? How does it work? Where is it useful? Find out after this break. Quantum computing is an emerging field at the intersection of computer science and quantum mechanics, promising to revolutionize how we process information. Unlike classical computers, which use bits as the basic unit of information, quantum computers use quantum bits, or qubits. Qubits take advantage of the principles of quantum mechanics, specifically superposition and entanglement, to perform complex computations more efficiently than classical systems. At the core of quantum computing is the concept of superposition. While classical bits are binary, existing as either 0 or 1, qubits can exist in a state that is both 0 and 1 simultaneously, thanks to superposition. This ability exponentially increases the computational power, as a system with n qubits can represent 2 to the n possible states at once. Another fundamental principle is entanglement, a quantum phenomenon where particles become interlinked in such a way that the state of one particle instantaneously influences the state of another, regardless of distance. Entangled qubits can perform coordinated operations that classical bits cannot, enabling complex problem-solving capabilities. The idea of quantum computing was first proposed in the early 1980s by physicist Richard Feynman and computer scientist David Deutsch. Feynman suggested that quantum systems could be simulated by quantum computers more efficiently than by classical computers. Deutsch further expanded on this by proposing the concept of a universal quantum computer. This theoretical model laid the groundwork for what has become a rapidly advancing field. Over the decades, significant progress has been made, albeit with considerable challenges. Building a quantum computer requires maintaining qubits in a coherent quantum state, which is extremely fragile. One approach to creating qubits is using superconducting circuits, as seen in the quantum processors developed by companies like IBM and Google. These circuits operate at temperatures near absolute zero to minimize decoherence. Another approach involves tapered ions, where ions are held in place using electromagnetic fields and manipulated with lasers. Companies like IonQ and academic institutions are pursuing this method. Quantum computers are not yet capable of outperforming classical computers in most tasks, a milestone known as quantum supremacy. However, in 2019, Google claimed to have achieved quantum supremacy with its Sycamore processor, which reportedly solved a specific problem faster than the world's most powerful classical supercomputer. While this claim has been met with skepticism and debate, it highlights the rapid advancements in the field. Currently, quantum computing is in a state of a noisy, intermediate-scale quantum devices, which means they can perform some quantum operations but are still prone to errors and limited in scale. Researchers are focused on improving qubit coherence times, developing better error correction algorithms, and scaling up the number of qubits. The potential applications of quantum computing are vast and transformative. One of the most promising areas is cryptography. Quantum computers could theoretically break widely used cryptographic schemes such as RSA and ECC by efficiently factoring large numbers and solving discrete logarithm problems. This has spurred research into post-quantum cryptography, which aims to develop cryptographic systems secure against quantum attacks. Quantum computing also holds promise in optimization problems, which are prevalent in industries like logistics, finance, and manufacturing. For example, quantum algorithms like the quantum approximate optimization algorithm can potentially solve complex optimization problems more efficiently than classical algorithms. In the field of material science and chemistry, quantum computers could simulate molecular structures and chemical reactions at an unprecedented level of detail. This capability could lead to the discovery of new materials, drugs, and catalysts, significantly advancing technology and medicine. Another exciting application is in artificial intelligence and machine learning. Quantum algorithms could accelerate the training of machine learning models, enabling more sophisticated AI systems and applications. Despite the promise, there are significant challenges to be addressed. The fragility of qubits necessitates robust error correction, which itself requires a large number of additional qubits, potentially thousands of physical qubits for each logical qubit. This scaling issue is a major hurdle in building practical large-scale quantum computers. Moreover, quantum computing requires specialized infrastructure, including ultra-low temperature environments and precise control mechanisms, which are costly and complex to maintain. This makes the development and deployment of quantum computers an expensive endeavor. As we look to the future, collaboration between academia, industry, and government is crucial for the advancement of quantum computing. Initiatives like the Quantum Internet Alliance and the U.S. National Quantum Initiative Act aim to foster research, development, and standardization in this field. Quantum computing is a transformative technology that leverages the principles of quantum mechanics to perform computations far beyond the reach of classical computers. While still in its early stages with significant technical and practical challenges to overcome, the potential applications in cryptography, optimization, material science, and AI make it a promising and exciting field. Continued research and innovation will be key to unlocking the full potential of quantum computing in the coming decades. That's all for this episode of Last Week in Science. I hope you enjoyed, and even more so, I hope you learned something. I'll see you the next time that science happens.